So this tokenized trained dataset is this. So this is very important. This is how we are going to make our own dataset, which is a bunch of text files, random text files, into a format that can be trained, that can be fine-tuned on the model. So it has the less three layers: the gate projection, the up projection, and the down projection. So gate projection. Hello everyone, welcome back to my channel. Today we are diving into something really exciting: fine-tuning Llama 2 model, which is one of the most powerful open source language models out there. But the cool part is that we are going to do it on our personal made dataset, which is a bunch of text files that you can find anywhere on the internet or you can generate yourself. We'll be using some clever techniques like LoRa, which basically lets us train just a tiny bit of the model's parameters while keeping all its original knowledge. Think of it like teaching an expert something without making them forget everything they already know. I'll be using the Hawaiian wildfire dataset as our example, but the techniques I'll be showing you today can be applied to pretty much any dataset you want to work with. Try out on anything you want to work with: CSV, be it tables, be it Excel files, be it PowerPoint presentations, be it Word documents, whatever you want to, you can do it. And we'll be using 4-bit quantization to preserve the model's memory footprint, and you can run it in Colab very, very easily. Okay, since I don't want to waste your time, here's the agenda for today. So let's dive right in. Okay, so the first thing is that we are going to install all the datasets. So the first thing is that we are going to install all the libraries that we'll need today. So let's do that. And also I would like to say before we start, just connect here and to change runtime type to make it T4 GPU, because you're going to need GPU for fine tuning, definitely. Yeah. Let's do reconnect. Sounds good. Now the next thing is let's install all the libraries that we'll need today. We're going to need PEFT. We are going to need accelerate. And I'll tell you why we'll need each of them. Just give me a moment. We'll need bits and bytes. We are going to need transformers, and we are going to need datasets. Okay, so let's discuss why we'll need each of these libraries in detail while these are loading. So PEFT, what is PEFT? PEFT is short form for parameter efficient fine tuning. So why is it needed? Because it will be needed to implement the LoRa, or the low rank adaptation. So what is that? Basically, it allows us to fine tune large models like Llama2, which has so many billions of parameters without updating all the parameters. And basically, we'll use LoRa config and get PEFT model parameters using the PEFT, which will help us to fine tune just a few low rank matrices of this entire 7 billion or 3 billion parameters that we have in total. I'll get into more detail as we're using the function, so hold your horses. Next one is pip install accelerate. So why do we need accelerate? Because for optimization and hardware utilization, these are all very important, because you have to remember that you are training a billion parameter model. Remember, it's a billion parameter model on these like GPUs and across different kinds of implementations on your laptop or on Google Colab, whatever you're doing. So you need to be as much efficient as possible, because you don't want to waste time, you don't want to lose memory, you want to save everything, you don't want to spend so much money without getting enough, back. That is why it's very important. So this accelerate helps to distribute training across GPUs, and it implements sort of like a precision training. So basically it speeds up the processing significantly. You don't need to know so much details, but overall a basic idea would be good. Next thing is the pip install bits and bytes. So bits and bytes is going to be sort of like the 4-bit quantization. We're going to use that. Okay, so the next thing is the transformers. So definitely transformers is the main library for transformer models. We are going to import auto tokenizer. We are going to import auto model for causal LM, and we are going to use Llama tokenizer trainer model, which is basically used for SFT training. We are going to do SFT training, which is basically supervised fine tuning. What do I mean by that? So it basically means that you're going to have a data set where you know what you're going to give the output as. For example, let's say we have an instruct model. like a chat model. We know a question, we know an answer. So we're going to provide a dataset in the form of a question answer format, Q&A format, or we're going to provide it like a text document format and then convert it, what we're going to do today. So we're going to give it a bunch of text documents, and these are all on like Hawaiian wildfire, what I found on the internet like randomly, but you can use it for anything you want. And maybe some kind of bot, some kind of agent, some kind of, I don't know, like some kind of HR questions, interview questions, whatever, like text documents. And you can make a model which is basically fine-tuned on that task so that it can answer on the documents, text documents perfectly. So that is what is the purpose of today's video. And this is what you're going to use it as. This trainer model can be found from the Transformers library. Cool. Now, next thing comes to the dataset. This is very simple. We're going to use the load dataset model, and we're going to do kind of dataset efficient loading and processing, pre-processing of dataset to make it in the way we want for our model to train on. So these packages, they work together to enable the efficient fine-tuning of large language models on basically limited hardware resources, which is exactly what our code is doing, because we don't have that many resources, many GPUs and everything. We have limited resources. So we are going to make the maximum use out of them. Great. So this is done. So now next thing we're going to need is pip install GPU util. So what does this do? So this basically does something like the GPU utilization. You will be able to, suppose you are not using Colab, because in Colab you have only one GPU, which is the T4 GPU. But suppose you are using your college servers, you are using somewhat like you have borrowed some kind of machines from your friend, from your company, you're working on the machines in your company. So anywhere you do this, it's very important to see what resources you have, how many GPUs you have at your hand, and how many you are able to use, what's the memory distribution you can do among the GPUs. Cool. So let's see. So import torch. Now we're going to have import GPU util. Now we're going to have import OS, which is our operating system. And now we're going to do GPU util dot show. Just remember this code. This is very important because this will help you forever to understand how many resources you have at your hand, how many you know what to use, and whether someone else is using it or not, whether there's a race condition or not, whether there's some issues, some thread running, daemon thread, which is the main thread that runs. So there's many problems here. So basically this gives you an idea of what you're dealing with, how much resources you have, and to what extent you can push your limits. So torch.CUDA is available. Yeah, so torch.CUDA is available, and we are going to do print GPU is available, and otherwise GPU not available. That's it. So this is the thing, and then now you're going to do is OS dot environment variable. So this basically sets the environment variable to what we want. So CUDA device order. This is going to be PCI bus ID. I'm going to explain what this means, but let me just complete writing this. CUDA visible devices is going to be 0 because there's only one device that's visible. Okay, so let's come back to this PCI bus ID actually. So this basically, what does it mean? So basically our CUDA basically provides two main methods for ordering or numbering the GPUs. So there can be many number of GPUs, right? This is just a general example because it has only one, you could have skipped that. But if you have many GPUs, it basically PCI bus ID numbers GPUs based on their PCI bus locations. So basically every GPU is connected to a computer's motherboard through the PCI. You don't need to understand in this detail. আওয়াজ করছিস কেন? এগুলো তো আসছে আওয়াজে। কি জ্বালানি বাবা। আর করতে হবে না আমাকে। So basically every GPU is connected to your mother's So basically every GPU is connected to your computer's motherboard through the PCI bus. So you don't need to understand this in so much detail, but it's sort of like a connection that you have, and it's used for ordering or numbering the GPUs. So this can help you when you have multiple GPUs, but otherwise it's fine. That's it. So let's move on. So let's run this and let's move on. So you will see what the resources look like when you're doing this. See, GPU is available and we have no usage of GPU right at the moment, but GPU is available and we can use it. Great. Sounds good. So now let's move on to the next thing. So we have import torch, we have import transformers. Oh, we've already imported torch, but that's okay. It doesn't matter. from transformers, we're going to import auto tokenizer and auto model for causal LM, and we are going to import bits and bytes config. Well, I did not want to auto-complete everything, but it doesn't matter. We are going to import Llama tokenizer. And from Hugging Face, next we are going to import from Hugging Face, because we'll need the model from there. And also, yeah, dataset is ours, but model we'll need from there. From Hugging Face, hub, import notebook login. You will need to log into the notebook because Llama model that we're going to use is actually, it needs to be given access to. So basically you will get access, don't worry about it. But there are a few steps. I'll show you all the steps, so don't worry about it. But it will take some time to get the access. So yeah, for me it took around 15 minutes, but for you might be longer. But yeah, you will get it within definitely few hours. So I'll come back to it. Wait. Now next thing is from PFT, import prepare model for k-bit training for 4-bit quantization. I'll come in detail, but this is what we need. And then we are going to need LoRa config. We're going to use LoRa for the 4-bit quantization, and then get PEFT model. And that's it. And then from, that's okay, we already have everything. Yeah. So let's move on. So if we are using Colab GPU, so which we are, so just give a short notice, this one, to say that if you're using your computer's GPU or something else, then this will not be activated. So yeah, so this is just to make your lives easier. And import output, we're going to be able to see the output properly. So that is why we are doing this. This actually enhances the output format a lot. Output.enable custom widget manager. Great. Sounds good. Now we are going to do is, now we're going to do the notebook login. Colab GPU in os.environment. We are going to do not equal to Hugging Face CLI login, and then else we're going to do notebook login. Let's see, we're going to do the Hugging Face login. Exactly. So this is the token. Go in here. Yeah. This is what your token. You can do yes, no, it's up to you. And now login is valid. It has been shared, and now the current active login is login. Great. Now you have logged in, so it now knows which models you have access to. Yeah. Now you can see right here. So these are the gated repositories that I have access to, and I have asked for the access to these models. So let me show you. So this is the model that we are going to use today, Meta Llama 2 7B chat. Right? So for this model, you need to get access. So if you see here, you have been granted access to this model. So otherwise, what you will see is, you will see a list of something. Let me see if I have access to this. If I don't have access to this, yeah, see, you need to share contact information with Meta to access the model. So this is what you will see when you are doing this chat thing, which I have already been granted access because I've run the code before. So this one you'll have to review, and then you have to give your first name, last name, date of birth, country, affiliation. It can be your college, it can be school, it can be the company you're working in, it can be anything. It doesn't really matter. And then just click submit and submit. That's it. You will get it within 15 minutes. You will see it appearing here. These are the models for which you've asked access for. So as you can see, this one, I haven't yet got access. I asked on October 4th. But yeah, that's okay. I don't really need it anymore. But this one I needed, so I got it really fast. So it will get accepted easily, I'm telling you. So just don't worry about it. And we can use it. Sounds good. Now, just you need to wait for a few minutes. Just wait here. That's it. Don't worry about it. Okay. So the next thing that comes is base model ID. So now we are going to provide the base model ID. So because on which we are going to do the fine tuning. This is going to be Meta Llama 2 7B chat HF. This one, which I just now said. For this, you will need access. So just get the access. Don't worry about it. BNB config. This is going to be the config in which we are going to load the model because we're going to do it in 4-bit quantization. So that's it. Bits and bytes config, and then it's going to be simple from here. Yeah. Let's see. Load in 4-bit. Load in 4-bit is true. BNB 4-bit use content double quant is true. And then we have 4-bit quant type NF4. And this is the compute D type, which is bfloat 16. What does it mean? Let me come in detail. So, okay. So 4-bit quantization, you can understand, we are going to load in 4-bit. That is why. So this basically means that we are going to do double quantization because it basically saves memory so much. So we were loading in 4-bit and then we are quantizing it again on top of it. So that is what is called double quantization. And this is because it will make it so much smaller without much loss in accuracy. We are not really looking for accuracy right now. But if you don't want to do this, you can do it too. You can just remove this line, comment out this line. It's up to you. And this is the quant type. So this is just like a quant type that we follow generally. So it basically uses this normal float 4, and NF4 is optimized for normal distributions in neural networks. So it basically preserves model accuracy as well. So we don't want to, because we're doing double quantization, this will lead to a big hit in the accuracy, but we are preserving that using NF4. So that's it. And this is just bfloat 16. This is the generally the data type that we generally use for fine tuning and for loading. So bfloat 16, remember this, bfloat 16. We're going to use it forever. Don't use float 16 normal. And don't use FP32. Don't use anything else, but use bfloat 16. Sounds good? Now let's load the model. Auto model for causal LM. Dot from pre-trained. Okay, auto model from causal LM dot from pre-trained. We are going to do the base model ID that we have already determined, written here, and then quantization config would be equal to BNB config. That's it. I don't need anything else. It's more than enough. BNB config. That's it. So quantization config is going to be BNB config. Let's load the model. Okay, I think I missed something. Let me see. Llama2 7B. Let me just copy this and it's a chat. It should have been chat. Yeah, sorry. Wait a second. Let me check. Right. HF. We need the Hugging Face type. HF is something we'll need. Otherwise, it will not work. This is something. This is a bit different model. There are a lot of variations. Yeah, see, now it's working. So this model we are going to load and we are going to fine tune this model on our personal data set, which is a bunch of text files. Cool. As long as this is waiting, so let's start writing the next part of the code. We don't want to waste time. Git clone. Let's see. I'll clone the repository here, which has a bunch of text files. So yeah. github.com polo club, and then I could find the easiest example, bunch of text documents online. So that is why I use this dataset. You can use anything. I'm telling you, you can use anything. This is the most simple thing ever possible. Let's see. Let me show you what the Git repository looks like. So we have data. See, there's just like a text document, normal text document talking about the Hawaiian wildfire. The first text document, the second text document, nothing. Like this, just a bunch of text documents. Simple, written, no formatting, no bullet points, nothing, literally, no tokens, anything. Just get whatever you want. It can be CSV file. I'm telling you, it can be CSV file, Word document, PDF documents. It can be Word documents. It can be Excel sheets, presentations, anything you want. All is fine. So this is what we are going to use today. This is going on. So this is the Git clone that we are going to do. And we're going to put it here. We are going to bring the dataset out because we don't want to put it inside this data repository because we're going to use the home repository. So let's do that as the next step. Yeah, we can do that when this cloning is done. But for now, let's write the next part of the code. So train dataset is going to be load dataset. Yeah, load dataset, and then this is going to be text. You're going to load text dataset, and data files is going to be train, and this is going to be a list. So list is going to be what? Content slash, well, it's correct, but it's not too much correct. Fine tuning LLM slash data slash Hawaii wf1.txt. This is the first one. And like this, we are having a lot of data. So how many data do we have? We have 10. We have 10, yeah, 10. So let me just copy this out 10 times. Or we can just use 2 for now. I mean, it's just for example purposes. So you can put in any number of data you want, and that's up to you. It's fine. Okay, let's keep 2 only. I don't want to make it too much complicated or I don't want it to take too much time, because again, this is because of training purposes, sample purposes. Split train. This sounds good. Now the train dataset is coming. Now the next thing that comes in is, yeah, its loading is done. The model loading is done. Now, yeah, I think because this has not been brought out, let me see. Yeah, we have here, and we have in data. Now we are going to bring it out outside. Are we have been able to? Okay, it doesn't really matter. It's inside this, right? So it's already in the, I think I lost something. Whatever, I don't want to waste too much time here. So let's just change it to 3. Let's just change it to 3, and let's just change it to 2 and 3. It is already there. So what's the issue? Train data files equal to train. Got it. So this is going to be a dictionary. Cool. So this is going to be a dictionary. Right. Okay. I think this is a dictionary, and this is going to be split train. I'm not very wrong. And Hawaii WF3. We have that. So why is it saying that? Is it a spelling mistake? WF3 content slash fine tuning LLMs slash data slash Hawaii WF3. Okay, I am not able to get why this is showing an error. Hawaii WF. Maybe I can make it 4 or something. Unable to find fine tuning. See, this kind of errors make your life so much difficult. Great, now it works. So we have the train split. Now the next thing we are going to do is train dataset text 0. So let's see an example. So in early morning of 9 coordinated the transaction. Let me see, which one did I take finally? It's the 4th one. See, this is the text coordinate transportation for people who. So this is how this data set has been created. So this text file has been broken down into lines, and each line constitutes a part of the data set. Let me, if you are not still believing me, let's see 1. See, had taken refuge. This entire thing is there in the second line, second element of the data set. So that's it. Now let's move on to the next one. So now we are going to do is tokenizer. So what is the step basically? So basically after getting the dataset, our next step is always to get the tokenizer and to tokenize the text document, the dataset. So that our next step is setting up the training arguments and all. and then choosing the correct library to train, and then start the training. And the next thing is inference, and then we are done. It's very simple. Just pay focus, and then literally by fine tuning is the next startup business in the next few years. So I mean, if you are really good at fine tuning, you can start your own startup as well. Let's see what you do with this information. So from pre-trained base model ID and used past equal to false, and then trust remote code equal to true, because you're using Hugging Face library, so you need to tell the Google Colab that it's able to trust the Hugging Face code. And you're going to add end of sequence token as true, because you will need the token ending. For why would we need the token ending? Well, because it helps to mark the end of the text sequences and it generates well-formed outputs. So use fast equal to false. Why are we doing that? Because it ensures consistent tokenization during fine-tuning. Otherwise, fast tokenizer is the Rust-based fast tokenizer, but it is not very efficient or accurate. So more reliable for Llama model is basically during fine-tuning to disable the fast one. Slower, but it prevents potential tokenization inconsistencies. And the US token is very important. So this will be really good. Okay, so now this part is very, very, very important. Pay close attention. Okay. Okay, so this thing is very important, what I'm going to talk about here. So this is basically specific to Llama models. So what do I mean by that? So basically here, if the pad token is none. So Llama models don't actually have the pad token. So that is why it's very important to provide the pad token to the tokenizer. Otherwise, Llama models won't work on uneven datasets. So it doesn't have any pad token. So just use end of sequence token as the pad token. So what we're going to do is tokenizer dot add special token as pad token, and then this pad token would be tokenizer dot end of sequence token, EOS token. That's it. You're loading the tokenizer and you are going to provide the pad token as the end of sequence token. Now we are going to make the tokenize. This is very important. This is how we are going to pre-process the dataset, which is our personal data. I think there was some timeout issue. Let me try it again. Okay, so these things now, they add special token. I am sorry. Yeah, done. So these things you need to keep in mind, because I mean, you have ChatGPT, you have Claude, sign, but still just keep in mind when you're doing an interviews or talking about in exams, whatever. So this tokenized trained dataset is this. So this is very important. This is how we are going to make our own dataset, which is a bunch of text files, random text files, into a format that can be trained, that can be fine-tuned on the model. So for phrase in train dataset is going to be tokenized train dataset dot append tokenizer phrase text. Okay, so what do I mean by this? So basically in the train dataset, we have the different kinds of phrases, right? So this is one phrase in the train dataset. See, this is a phrase, right? This is not a complete sentence, this is a phrase. And tokenized train dataset will append the tokenized version of this text. So, okay, so let's see an example how this looks like. So let's see an example. Let's first run this, and then let's see tokenized train dataset 1. See, so this is a tokenized train dataset that our model is able to understand, because it needs to be in a format that our model is able to understand. Otherwise, it's impossible for the model to basically convert random text files into something to fine tune. So look at this. So this is basically all the different IDs. This has been broken down into individual tokens. It can be had, taken, refugee, or it can be had, taken as one token, refugee second token, in the as a third token, and whatever. It has its own vocabulary, and based on that, it is able to convert this into the input IDs. So these are all the different input IDs, and this is the attention mask. So what do I mean by the attention mask? So this attention mask means that this input ID specifically, input ID is basically the token. Okay, so don't worry about it. Don't think it's something else. So this is basically the token that will be used, and this is the numerical representation of the text. So had taken is represented as 1, refuge is represented as 750 based on the vocabulary of this model and this tokenizer. And then the attention mask is basically all are 1 because this has not been padded. So suppose there's a token that has been padded. Let's see an example. You will see the pad token at the end, and in that case, this is also not padded. But if you are padding a basically dataset or a line, then the attention mask will all be 0 after that, and it will be all with the pad token. So we don't know the pad token exactly what the token is. It's the EOS token. So let's see what it looks like. EOS token. Do like your own experiments, because otherwise it's very difficult for you to understand everything based on like listening knowledge or theory. This is the best way to learn. So tokenizer.us token is this. So this is the pad token as well. So this here you will see all this based on the numerical, and then the tension mask. Sounds good. Now we are going to do the model.gradient checkpointing. Now the part comes where we're going to train the model, because we have loaded the tokenizer and we have converted our model, our dataset into tokens, and then we're all ready to go. We have the dataset, we have the tokenizer, now we just need the model. So this is going to be checkpointing.enable, and then model is going to be prepare model for k-bit training model. Now it's going to be config equal to LoRa config. So LoRa config is going to be r equal to 0. I'm going to talk about every of these parameters in detail. So let me just complete it. LoRa alpha is going to be not 0, but 64. And then the target models are going to be Q proj, K proj, V proj, gate proj. Proj means projection. I'll discuss it. I'll discuss this in great detail. So that you can able to understand this bit. Up proj and then O proj. Yeah, we have total 7. And then bias is going to be none. Bias is going to be none. And then LoRa dropout is going to be 0.05. And then the task type is going to be causal LM. So the autocomplete is not really good here, but yeah. So this is the get PEFT model, and then config. Okay, sounds good. I think I did some issue model.gradient checkpointing.enable. Okay, so again, I would suggest you to just use explain error here in Gemini, or you can use it on ChatGPT, whatever you want, but it's all okay. So here the issue I know is that it's going to be checkpoint. Yeah, this you can do either, or you can do checkpointing enable, both works. And then, okay, sorry. So this is not 0, this should be 8. Okay, so let's dive into the details of each and every parameter here. Okay, so R equal to 0, R equal to 8. So R equal to 8 is a good balance for most tasks, because lower R means that it's going to be less expressive. And basically, R equal to 8 means update matrices are rank 8. So what do I mean by that? So let us see the transformer example. So then we'll be able to understand better. So the high level transformer block structure is this. So here you have the input text, and then you have the attention block. And inside the attention block, you have 2 layers. So you have the multi-head attention, and then which feeds the output into the feed forward network, or FFN. So let's dive into the multi-head attention now. So this is the multi-head attention detail. So you have the input, you have the linear layers. Now we have the query, key, and value. So these are the ones that are targeted because these are very important. And next is the attention scores, and then it now goes through the O projection, which is the output projection. So this is also targeted because these are the, like, it targets basically the update or rank matrices of specific layers which are the most important. So what do we mean by the query projection layer? So let's discuss that. So query projection layer is basically the projects the input into the question space. So for example, let's say we have what happened in Hawaii. It becomes a query vector. So now the original is going to be, suppose, 768 cross 768 matrix. And with LoRa, it's going to be 2 768 cross 8 and 8 cross 768 matrix, because we have R equal to 8, which is the rank. So this way, this is broken down into smaller matrices, because large matrices are very difficult to deal with. So this breaks it down to smaller matrices. Try to understand. This is very, very important, and this will clear everything you have doubt in. Now the key projection or K projection. So this projects the input to answer lookup space. So what do I mean by that? So basically it transforms the text into searchable keys. So basically, suppose we have what happens in Hawaii. Now it knows that Hawaii is connected to this, 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 this. So this is like a key value pair, right? So you have Hawaii, and Hawaii is projected to the wildfire. It has projected to the forest, whatever it is. So you have a key lookup pair. So, and the next thing is the value projection. So the value projection is basically, it projects the input to the answer space, and it transforms the text into actual information that will help us. So let's discuss, let's summarize. The first thing is query projection. It projects the query, what happened in Hawaii, what is a wildfire, and all this into a kind of token that is able to, that helps us to understand it, that helps the computer to understand it. Next thing is the K projection or the key projection. It transforms the text into searchable keys. And third thing is the V projection or value projection, which transforms the actual, gives me the answer to the problem. And now the output projection, it basically combines and transforms and filters the output such a way that we are able to understand in our own language. Next thing is the feed forward network. So it has the less three layers: the gate projection, the up projection, and the down projection. So gate projection, it controls the information flow, acts like a smart filter. There are guardrails, there are this not to be said, there are some kind of passwords. These are not to be shared at all. So these are the gate projection. Next thing is the up projection, which means expands the information. And we also need a down projection because we are able to control these parameters based on what our dataset looks like. This is very important. This basically clears everything that you have doubt in, because we have up projection, gate projection, upward projection, downward projection. We have Q projection, query projection, key projection, and value projection. We have an understanding of every one of these 7 projections. That's it. Basically, that's it. That is enough for your interview and everything that you need to know, even for research purposes as well. This is enough. And okay, so great. So now we have the PEFT model. We know what everything does here. And now we are going to train the model. So let's do that. Trainer equal to transformers dot trainer. And this is going to be model equal to model. And then it's going to be trained dataset equal to tokenized trained dataset, which is going to be args equal to transformers dot training arguments, and then we need the output directory as / fine-tuned model. Now it's going to be per device trained batch size as, let's say, it's 2 to make it faster. This is a batch size. Like if it's larger batch size, then 2 will be done in each iteration. Otherwise, it's whatever, it can be 1. And next thing is num train epochs, total iterations we want to run it for. Total we want to run it for 3. We have learning rate as 1e minus 4, 10 to the power minus 4. And we have max steps. I don't want to run it more than 20, but listen to me. You will be running it for at least 1500 steps. Just let it be there, run there for some time, because I want to finish it fast. That is why I'm doing it 20. But you need to do it at least for 1000 steps or 1500 steps to actually see valuable things coming out of it. Okay, so now next thing is BF16 is going to be false. Here we're not going to use BF16. I mean, you can use BF16, but we want to see what happens without BF16 as well, because we're already doing double quantization before, as I showed you. Remember? Yeah, already using double quantization. So it's fine at the end to not use PF16, to use a standard FP32. Now Optim is going to be this is a new thing. So I'm going to discuss this a little bit. 8-bit, something you can use or you cannot use, whatever, it's fine. And now it's coming out to be the logging directory, to be the log. And you have the save strategy as epoch. And you have the save steps as 50. It's fine. If you're doing for 1500 or 2000 data points, then it's very important to do this to 50 because you want to see what's going on, whether loss is decreasing, loss is increasing, whether you need to change any kind of other hyperparameters or not. But yeah. And then you have this. And then the next thing is you need the data collator. So this is something I'll need to explain to you in greater detail. So be ready. So I'll just finish this and then we will discuss. Data collator for language model link as tokenizer MLM equal to false. And then we have the normal thing like model config dot use cache equal to false. And then we have the trainer dot train. So I'm going to let it running and I'm going to explain all these in great detail. And I did a spelling mistake. Okay, sounds good. Okay, model config is not defined. Sorry, it's going to be model.config. That's all right. Okay, now let's discuss. Let's discuss all this in detail. Okay. So definitely the model you can understand, then the dataset you can understand, then the batch size you know too, and gradient accumulation steps is 2. So remember this. Gradient accumulation step is basically batch processing flow. So it's basically how we are processing the entire dataset. So basically in the iteration 1, we're going to do a forward pass and we're going to have the gradient calculated and stored. And the second iteration, we're going to do again a forward pass and then we have again the gradient calculated. And then these two gradients, we're going to combine and then do the model update. We're not going to do it in between. So this is what is called the gradient accumulation steps is 2. So you're going to remember the gradient that is calculated. It's going to combine the two gradients to kind of specific formula. And then it's going to update the model. So this is the gradient accumulation steps. You can change as you want it, but it's better to keep it as 2 because it's the most standard. And then you can play with it. I would encourage you to play with it because your interview might ask you to do this, to do that. And it's very important that you have a good knowledge of this because this is our future. And then comes the numtrain epochs is 3, runs through the entire dataset 3 times. And next is max steps is 20. So it stops after 20 update steps. And then you have the learning rate at 10 to the power -4, which means a small learning rate for fine tuning is fine. You don't want to overfit and you don't want to, you want it to be studied incrementally. And bflow16 is not being used, that's okay. Now this is very important. Optim paged Adam W. Optimizer is paged Adam W 8-bit. So this is a memory efficient Adam W optimizer. So standard Adam W means that all the parameters and optimizer states are in memory. But paged 8-bit Adam W means that model parameters are basically like paged optimizer states. They are 8-bit quantized states that are in memory. It's not the entire thing is in memory. We don't want the entire thing because anyway we're not training it, we're not loading it in the full memory and it's not possible, not needed. So you don't want to waste things. So basically this optimizer is for the 8-bit quantized states and the rest is very simple to understand. Now comes the data collator, which is very important. The data collator is basically what it does is it has like an input sequence. So sequence 1 has a lot of tokens. Total tokens is, suppose it's 50. And sequence 2 has a total tokens as 30. So what collator does is finds the max length, which is 50. Basically, the padding thing is done by the data collator, which is very, very, very important. I cannot stress it enough. This is important to have a optimized data set, which is of the same length, of the same width, not same length, of the same width throughout, so that it's able to learn everything perfectly. So the same max length is going to be 50. And now we're going to do pad the shorter sequences. Basically, I showed you the input tokens are going to be comma and then pad token, whatever it is. And then the attention mask is going to be 0, 0, 0 because it's the padding thing we don't want it to learn. But we want the data set to be of the same width. I hope you understand this. So this is the final complete training flow. Remember this very well. So data flow during training. First, raw text, Hawaii fires. Next thing is tokenization. Next thing is data collation. Next thing is patching. Then comes forward pass. Then is the calculate loss. And then is the accumulate gradients, and then update weights, and then save checkpoints. That's it. You have the model and then inference. Very, very simple and very, very like great. Okay, I will need to provide an API key. I'm going to blur this out, but you just go. I've got my API key. It's absolutely free. It helps you to keep a track of what weights are there, how much you have trained, what is the current status, and everything. Great. I think we have everything here. Now we just need the inference, and then we are done. So let's start writing the inference as it's calculating the loss. So I'm going to write it in a separate way because we often have like in Python files when we are doing it, then we have it in different files. We have a train.py and we have a test.py, standard like nomenclature. So that is why I'm making the import statements again. So we are going to do import torch, and then from transformers, import auto tokenizer and auto model for causal LM. Next thing is from transformers, import bits and bytes config Llama tokenizer. Understand this inference thing as well, because if you train a model and it's perfect, it's great. But you don't know how to inference it, then just throw it in the dustbin. From PEFT import PEFT model. Next thing that comes is base model ID is going to be, yeah, this is done. So obviously the losses decrease, but it can go a lot less because I stopped it at 20. Just do it till 1000 and you will see the difference, guaranteed. Base model ID is going to be the same thing, and I'm not going to write it again. So this is the thing. I'm going to share all the links in the description, so don't worry about it. And now it comes the NF4 config, normal float 4 config, because we're doing it in 4-bit quantization, that is why. Bits and bytes config. Now we have load in. I really don't think we need to write this again. Let's copy paste. And we have it here. There you go. We have load in 4-bit as 4. We have BNB 4-bit use double quant as true. We have BNB 4-bit quant type as NF4, and we have the data type as B floor 16. I hope you know this. I've already talked about it, so I think it's okay. I think there's a spelling mistake I have here. So this is very important. Now the next thing is tokenizer equal to Llama. You have to do the entire same thing. The way you did the pre-processing there, you're going to do it here, because that is how the model recognizes the text, and that is how the model is able to give the answer. Okay. Okay, now we have the from pre-trained, and you have base model ID. You have use fast. I think we can use this. Let's see. Yes, add US token as true. Do the same thing, exactly the same thing that you have done during training, if you really want your model to succeed. Well, if you don't, then it's fine. But I'm just saying that you need use fast is false, and then trust remote code as true, and then add US token as true. Now this is just auto completed, but yeah, we can use it. I think so. We can use it. Base model is going to be auto model for causal LM. Dot from pre-trained, we have the base model ID. Let's put it in next line. We have the quantization config as NF4 config, and we have the device map as auto. Whatever it's going to use CUDA, but it's fine. And you have the trust remote code as true, and you have the use auth token as true because it's loading from the model, so it's fine. Loading from the Hugging Face, so it's fine. Auth token as true. I think I did some mistake. Bits and bytes. Yep. Yeah, so it loads the base model, and now it's going to load the tokenizer for the base model. And this is the tokenizer that we're going to use for the fine-tune model as well, because we have made no changes in the tokenizer. tokenizer is llama tokenizer dot from pre-trained base model ID, use fast is false, trust remote code equal to true, and then this is fine. And then we are going to do is model fine-tuned equal to PEFT model dot from pre-trained base model, and then we have a directory, as you know, fine-tuned model slash checkpoint 20. Because we are going to use the last checkpoint. You're going to use 1500,000, whatever you have it, and that's all right. That's up to you what you want to use. Now we are going to see something cool. Now we're going to see the inference. So let's say user question is going to be, okay, there's some problem here. Think there's some problem here. What is the problem here? We did save it here, and do we not see it here? Should have been dot slash. Yep, that's what caused the problem, I think. No, wait, we have the fine-tuned model here. Also, that is because it just now made. Got it. So let's see. So what was the error here? You need to provide the bad token. Yep, let's load this. Now let's get this and then this. Yeah, so we have the pad token here and we have the data collator, and this will going to generate the output inside this, and we have the logs inside this generating. These are all the logs. It's very important if you want to see what went wrong. And while this is happening, this is the way we are going to do the inference. And it was not able to find it because, well, it's not there. Cool. So as long as it's running, let's get this running and this running next to next. And now let's start typing the output. We'll see if again error comes then. So when did wildfires start? So this is a very valid question based on our prompt, and it has been trained on that, so it should be able to answer it. So this is going to be the evaluate prompt as, let me see, F question is user question, and then we need to have something like just answer this question accurately and concisely. That's it. We don't need anything else. It's the evaluate prompt. And the next thing is that we need to tokenize the prompt, because you remember we tokenize the dataset. So if we tokenize the dataset, we need to tokenize the prompt as well. Eval prompt and return tensors pt. Basically, we are going to return the form of tensor. That is why we do this. Remember this. Don't forget about it. And then we are going to change it to CUDA. And then we are going to do model fine-tuned, fine-tuned dot eval. That's it. And then very simply torch.nograd. We don't want to generate the gradients and all, so it's fine. We don't need the gradients, so it's fine to just check that out. Tokenizer.decode model fine-tune.generate prompt tokenized, and then max new tokens is whatever 100. Let's not keep it 100. Let's increase it a little bit, 1024. And then skip special tokens is true. Special tokens are like bad and we don't really need them, so it's fine to just check them out. And then we have the torch.cuda.empty cache. We don't want to keep the cache either. So I'm not sure what happened. Let's see. This is done. Now this is getting loaded. And it's going to just see this and try to understand this. I'm going to discuss everything in detail. Yeah, just see this and try to understand this. So what did we do? We needed the base model here because the fine-tuned model is just a bunch of LoRa configs and these projection vectors that have been trained. So these projection vectors need to be sort of merged with the base model. So what we are doing here, PFT model is basically from pre-trained. So we have the base model and we have the fine-tuned weights. And then these two are going to be combined together to create this model fine-tuned on which we are going to run the inference. Now, suppose if it was we were not using LoRa or we were not using QLoRa, we were just doing a normal thing, normal, the whole fine tuning, then we did not have needed this because PFT model we would not be using. We are not using any quantized version. We are not using anything. So that is why it's very important. I hope you understand my point. So this is the PFT model, fine tune model is checkpoint 20. And now this is the answer. So see, there's the answer that is coming in because this has been trained on the dataset now and it gets this start and the common occurrence, and then important to note that they are common. So this is how we are going to be able to fine tune the data. Sounds good? I think you got the whole point. So if you have any questions, don't forget to put them in the comment section and I'll get back to you. I am very active on YouTube and I try to answer all doubts that you have. And yeah, like, subscribe, and comment and share with your friends and all. And yeah, let's see you in the next one. Take care. Bye.